Welcome, everyone. Thanks for joining us for another deep dive. Today, our mission is to explore the real foundations of generative AI by looking at some cutting-edge, state-of-the-art research.
Yeah, we have a really fantastic paper today.
We do. We are digging into a fascinating 2026 paper. It's called Beyond Domains, Reusing Web Skills via Transferable Interaction Patterns. And this is from a major collaboration, researchers from the University of Michigan, Alibaba Group, Purdue, McMaster, and UPenn.
It's a powerhouse team, honestly.
Yeah.
And the problem they are tackling is something that is going to affect how you, as the listener, actually interact with AI every single day.
Right. So to set this up, I want you to imagine you're sitting in a self-driving car.
Okay.
And you tell, take me to the grocery store.
Mm.
But instead of just smoothly driving down the road, the car completely stops at every single telephone pole.
Oh, wow. That sounds terrible.
It is. It stops. It takes a high-resolution 360-degree picture of the street, sends that massive image to some supercomputer in another state, waits for the computer to analyze the entire neighborhood just to get permission to drive another 10 feet, and then it does the whole process all over again at the next pole.
I mean, I guess it might technically get you to the grocery store eventually, assuming you don't run out of patience first.
Yeah.
Or, run out of money to pay for that supercomputer.
Exactly. It is a wildly inefficient way to travel. But when you look at the current world of modern generative AI web agents, that stop-and-go car is exactly what we're dealing with.
Yeah, that is the perfect analogy for where we are right now.
It's an automation landscape that is brilliant,
Yeah.
but incredibly bottlenecked by its own intelligence. So if you want an AI assistant that can browse the web for you, do your shopping, or fill out boring admin forms, this is the hurdle we have to clear.
Okay, let's unpack this. Why exactly does this bottleneck exist? Well, to understand the delay, you really have to look at the current standard setup for web agents, which is heavily based on what's called the React paradigm.
And React stands for reasoning and acting, right?
Spot on, yeah. In this setup, the LLM, the large language model, acts as a tool caller. So it's not just passively chatting with you. It essentially has virtual hands. It can click a button, it can type a word into a text box, or it can scroll.
Which is awesome.
Mm.
But the catch is how it decides to take those actions.
Right. Because for every single one of those microscopic movements, the LLM is forced to read a fresh snapshot of the page.
Wait, a fresh snapshot for every single click?
Every single action. It evaluates the entire page structure, thinks about your overarching goal, decides to, just click one text box, and then it stops.
That's agonizing.
It is. The web page updates, maybe just highlights the box it clicked. But then the AI has to read the entire new page all over again, generating what researchers call a policy-facing LLM completion, just to decide to type the first word.
Okay, so it's doing deep, resource-heavy philosophy just to click a checkbox.
Basically, yes. It's pulling all that website data into its context window, computing probabilities, and spitting out one tiny action. If it's filling out a basic form with 5 boxes, it's paying that computational toll 5 separate times.
Which explains the cost. I mean, on long tasks, these completions must just pile up.
They dominate the process. When they run agents on big benchmarks like Mind2Web or Web Arena, this step-by-step thinking tax takes up almost all the time and money.
It's like navigating a new city by stopping at every single street corner, pulling out a massive map, finding your exact latitude and longitude, and asking for directions.
Right. Instead of just recognizing the general flow of a neighborhood and walking naturally. The AI doesn't have any intuition. It completely lacks muscle memory. And this hyper-reliance on the central LLM is exactly what researchers want to fix.
So if the constant reasoning is the problem, I assume researchers have tried to give the AI some kind of memory or reflexes before.
Oh, absolutely. They've tried building what they call reusable web skills. You can think of them as macros, built from successful past actions.
So instead of calling the LLM for 5 tiny steps, it just calls one macro skill.
Exactly. It's a highly logical fix. You pay the LLM once, and it executes a whole sequence smoothly.
Sounds like problem solved. But I'm guessing it wasn't that easy.
Not at all. The paper details 2 previous state-of-the-art approaches, and they both had fatal flaws when tested on the open web.
Okay, let's hear them.
First was same website reuse. This was used by systems like SkillWeaver or ASI. The AI learns a really effective skill for, say, booking a flight on one specific airline's website.
Let me guess. If you go to a different airline, it completely breaks.
It completely freezes. The skill is entirely tied to that exact site's interface. If the web designer moves the Book Now button slightly or renames it, the macro is useless.
Because it's just looking for the exact code it memorized.
Right. So to fix that, researchers tried same domain reuse. Systems like Polyskill did this.
That sounds a bit more flexible.
It is a step better. It abstracts the interfaces a bit, so a skill learned on one shoe store might work on a clothing store. It understands the general vibe of a shopping cart.
But it's strictly confined to shopping, isn't it?
Exactly. A shopping skill only works on shopping sites, period.
And the data from the sources really backs this up. I was looking at Figure 2 in the paper, and it's striking. When the tasks move from cross-task on familiar sites to cross-domain, so totally new types of websites, the skill reuse rate just drops off a cliff.
It really does. For the ASI model, it plummets from 32% down to 14%.
And SkillWeaver crashes to just 8%. And the moment they drop those skills, the average number of those expensive LLM steps spikes right back up.
Yeah, it reverts back to that slow, step-by-step React reasoning because it's confused.
But here's my question. Why is the AI so rigid? Because as a human, if I know how to buy a pair of shoes online, I can easily figure out how to, submit a help ticket on a completely different website.
Right, the domains are totally different.
Yeah. I mean, a shoe store and an IT desk have nothing in common semantically, but I don't suddenly forget how to use a web browser. Why can't the AI see that connection?
And that question right there is the core insight of this entire paper. That's the aha moment. The researchers introduced a system called SkillMigrator to answer exactly that.
Okay, so how does SkillMigrator do it?
It learns to transfer skills by matching the layout structure of a page. Rather than looking at specific text labels or hidden website code, it prioritizes structure over semantics.
This is the most fascinating part of the paper to me. They laid out this brilliant visual example, Figure 1. Let's break this down for everyone listening because it really clicks once you hear it.
Yeah, go for it.
So imagine 3 completely different websites. First, you have Shopify, an e-commerce site, and you want to add a new product.
Okay.
Second, you have GitLab, which is for software developers, and you need to open a new issue. And third, you have PostMill, an online forum, and you want to create a new forum.
Right, so textually, those 3 sites have absolutely nothing in common.
Exactly. The words, the purpose, the domains, completely different. But structurally, they're the exact same programmatic pattern.
They really are.
On Shopify, you fill in a title and description, and you click Save. On GitLab, title, description, and click Create. It's always just fill a few labeled inputs, then click a single Submit button at the bottom.
And that's where previous systems failed. They got stuck because one button said Save and the other said Create. SkillMigrator ignores that. To do this, it uses a new type of memory unit called a TIP.
A TIP. What does that stand for?
Transferable interaction pattern. It's basically the system's abstract blueprint of a skill, and it has 4 components.
Okay, walk me through them.
First is the intent. This is just the natural language goal, like a fill out this form. Second is the operation template, which is the actual physical action, like a fill and submit sequence.
Makes sense. What's the third?
Third is the slot schema. This is what needs filling in. But the genius part is that it's equipped with a pool of synonyms.
Oh, wow. So it's not looking for one specific word.
Exactly. It knows mathematically that title, subject, and summary all serve the exact same function on a form.
That's incredibly smart. It stops the AI from breaking just because a web designer used a weird word.
Right. And the fourth component is the tree skeleton. This is a structural sketch of the page's HTML from when the skill was first learned. It's the literal architecture.
Okay, so it has this library of TIPs, these architectural blueprints. But how does it actually find the right skill when you drop it onto a brand new website?
It uses a retrieval scoring system, which they show in equation 3 of the paper. It combines 2 signals. First is the text signal, so what did you actually ask the AI to do?
Right, matching the prompt to the intent.
But then it adds the crucial second part, the layout signal. What does the live page actually look like? To figure that out, it calculates what's called the tree edit distance.
Tree edit distance. Let's explain this, because how an AI sees a page layout is super interesting.
Yeah, so imagine the web page's code is like a family tree of boxes. You have a big box for the form, smaller boxes inside for the text fields, and a box at the bottom for the submit button.
Just nesting boxes.
Exactly. Tree edit distance just calculates how many edits, like adding a box or removing one, it would take to make the saved blueprint in its memory perfectly match the live page you are looking at right now.
So if the saved memory expects 3 boxes, but the live page has 4, that's just one edit.
Right. And if the number of edits is really low, the AI knows the architecture is a match, even if the words are totally foreign.
But wait, what if the page is just radically different, like a super experimental design? We don't want the AI just wildly guessing and clicking things if the edit distance is huge.
Definitely not. And that's why they built in a safety valve. It's a gate threshold, represented by the Greek letter beta.
This is basically the AI's internal confidence meter, right?
Exactly. If the combined score of the text and layout falls below that beta threshold, the AI just says, I don't recognize this pattern. It aborts the quick skill and safely falls back to reading the page step by step.
I love that. It admits when it's confused instead of hallucinating. But let's say the score is high, clears the threshold. How does it actually execute the skill?
It happens in 2 stages, stage A and stage B. The paper uses a great example of writing a product review.
Okay, let's use that. Say I tell the AI, write a review, put great fit as the summary, and write a detailed comment about the material.
So stage A is the value parse. The AI pulls the exact text from your instruction. It grabs great fit and mentally assigns it to the abstract concept of a title.
It's just holding those variables, getting ready.
Right. Then it moves to stage B, slot binding. The AI looks at the live page to find where to put the text. Thanks to that synonym pool, it sees a box labeled post title or summary and instantly knows that means title.
So it binds great fit to that specific box.
Yes. And it binds your comment to the main box and it binds its click to the submit button.
And here is the really cool quirk about stage B, the variable arity.
Yes, variable arity is brilliant.
Because let's say the save skill was for a form with 5 boxes. But the new website only has 2 boxes. It perfectly adapts. It just fills the 2 that exist and ignores the rest. It doesn't crash trying to find boxes that aren't there.
It is so robust, it naturally molds to the constraints of the new environment.
So what does this all mean? When they actually ran SkillMigrator on these massive punishing benchmarks, did it work?
It worked incredibly well. On WebArena and Mind2Web, it reduced the average LLM action count on successful tasks by 8 to 10% compared to the absolute best baselines.
That is a massive reduction in processing time and cost.
And it did that while completely maintaining the task's success rate. No drop in accuracy.
But I think the biggest takeaway for the industry is what they call the orthogonality bonus.
Yeah, this is huge for practical application. A SkillMigrator doesn't have to replace older systems like PolySkill.
They can just sit right on top of them.
Exactly. As a retrieval layer, it tries to find a structural match across domains first. If it can't, it just hands it off to PolySkill to handle it within a known domain.
And when they combine them like that, what happened?
They got the lowest average LLM action count in the entire suite of tests, down to just 5.3 actions.
That's incredible. And just to be clear, this isn't some quirk of GPT-4, right? The architecture is completely model agnostic.
Totally agnostic. They actually swapped out the brain. They took out GPT 4.1 and plugged in Claude 4.
And Claude 4's success rate actually jumped to 54.7%, up from 45.7%. It proves that focusing on layout structure works no matter what LLM is driving it. Which brings us to why you, listening to this, should actually care about all these slot schemas and edit distances. Right now, AI web agents are kind of expensive, clunky novelties.
Yeah, they look great in a demo, but they fall apart in the real world.
Exactly. But this research is the crucial bridge. This is how we get to the future of fast, cheap, reliable personal AI assistants that can actually navigate the entire open web for you.
It saves you time. It saves developers massive computing costs. We are moving from AI that slowly reads every word to an AI that intuitively sees the structural matrix of the web.
It really is a huge leap. But, whenever we talk about changing how agents navigate the internet, we have to think about the downstream effects.
Right. And there is a really provocative thought here that goes beyond the paper.
Let's hear it.
If AI agents are now navigating entirely by recognizing structural layouts and calculating tree edit distances, what happens to web design in the future?
Oh, that's interesting, because right now, developers build sites for human eyes and for search engines.
Exactly. But if agents are doing all the browsing and buying, will developers start deliberately standardizing their layout specifically for AI?
Wow. Or, wait, they could intentionally obfuscate them? Like, if you want to stop AI from scraping your data, you just scramble your layout structure with invisible junk code to inflate the edit distance.
Make the confidence meter fail on purpose. It could be the birth of a whole new industry. Instead of SEO, we might be looking at ALO agent layout optimization.
Designing the web, not for human aesthetics, but specifically to manipulate how AI agents interact with it. That is a wild thought to end on.
It really changes how you look at a web page.
It does. We went from a self-driving car stopping at every pole to look at a map, to an AI that finally just looks at the shape of the road and drives. But the real question now is, who gets to draw the map in the future?
Absolutely.
Well, thank you so much for joining us on this deep dive into the foundations of generative AI. We hope you walk away with a clearer picture of how the web's evolving, and we invite you to ponder what a digital world optimized for agents might actually look like. Until next time.